Welcome back to the Deep Dive. This is the place where we take stacks of incredibly dense source material, your articles, your research, your notes, and we try to filter out the signal, giving you the architectural knowledge you need without you having to spend weeks chasing down documentation.
Today, we are strapping in for what I really consider the most fundamental exploration you can do.
Yeah.
This is what's required to move from being, an effective programmer to becoming a true senior platform engineer.
Right.
We are going to move way past the surface level of just talking about tools and dive right into the why. Why are specific architectural choices, those really critical trade-offs, why are they made when you're building truly scalable and reliable systems?
That's exactly right.
Yeah.
Our mission today is not just to list off a bunch of definitions. We are here to unpack those foundational concepts that govern modern system performance, reliability, and I think most importantly, how you manage the complexity that just inevitably comes with scale.
It does.
We have sources covering, well, everything. From the absolute execution core, like how software actually runs, all the way up to these abstract software design principles, like the critical solid rules.
It's an exhaustive map, for sure. And as with any complex architecture, you really have to start right at the foundation before we can even begin to talk about microservices or containers or, global hosting.
Yeah, you need the bedrock first.
You do.
Yeah.
We need to understand how software executes instructions at the lowest level. And that means starting with the absolute core of concurrency, processes and threads.
Okay, let's unpack this core concept first because this distinction is just so critical for performance and for stability. When a computer runs a program, you immediately hear these two terms, processes and threads. They often get mixed up, but their difference really determines the isolation boundaries of your entire application. So, to start, what truly defines a process?
Okay, so a process is the running program itself. Think of it as an entirely independent instance. I like the analogy of a self-contained spaceship.
A spaceship, okay.
It's a completely isolated bubble of execution, totally separate from everything else that's happening on the machine. And when we look at what makes up that spaceship, all of its resources are dedicated and unique to that single process.
And what are those dedicated resources, specifically? What's inside the bubble?
Primarily, and this is the most crucial part, its own dedicated virtual memory space. It also has a specific set of file descriptors, its own distinct set of environment variables, and critically, its own security context. Everything it needs to operate is contained right there within its own isolated walls.
So if you launch two separate applications or even, say, two separate instances of the same app, like you open two windows of a big video editor, those are two completely separate, insulated processes.
Precisely. And the key benefit of that isolation is fault tolerance. It's huge. If one process encounters some catastrophic failure, it runs out of memory or hits a core bug, whatever, it generally doesn't affect the other processes running on the machine.
So your whole computer doesn't crash.
Right. That strong isolation is why your operating system, by its very design, launches major applications as separate processes. It's all about providing resilience.
But wait a second. If they are so perfectly isolated, so separate, how do these processes ever talk to each other? For example, that video editor might need to communicate with a file explorer process to open a file.
And that's where we hit the first crucial point of friction. It's a great question. If processes need to communicate, they can't just look into each other's memory. It's forbidden. They have to use explicit interprocess communication, or IPC, mechanism.
Okay, so it's not automatic. You have to build it.
You have to engineer it, and it costs time. It has overhead.
So what are the typical engineering solutions for that, for IPC?
Well, common examples would be using network sockets, even if they're just local sockets on the same machine, or setting up what are called pipelines for sequential data transfer. Or you can carve out very specific small areas of shared memory that both processes explicitly agree to look at.
But it's always slower, right?
It's inherently slower and more complex than just talking to yourself, so to speak. But the trade-off is that it preserves that critical isolation and that fault tolerance we were talking about.
Okay, that makes sense. So now let's bring in the thread. If the process is the whole spaceship, what is a thread in that context?
A thread is the actual unit of execution that's operating within that single parent process. So the process is the house. You can think of the threads as the specialized workers who are all living and working inside that same house.
And the key difference is they're not isolated from each other.
That's the critical characteristic. It's the one thing that defines the entire trade-off landscape. Threads share the same memory space and resources of their parent process.
Ah, okay. So processes live in completely separate houses, But all the threads are basically roommates. They're sharing the same kitchen, the same tools, and that same central pool of memory.
Exactly. And because they're sharing, communication between threads is nearly instantaneous. They're simply reading and writing to the same locations in memory. They don't need any of those heavy IPC mechanisms.
So that's the big performance win.
It's a massive performance advantage. That speed is why you use threads. However, and this is a big however, this speed comes at a significant and often painful cost. Risk. Because they are simultaneously operating on shared data, you open your application up to a whole class of potential issues. Issues that can lead to catastrophic application failure if you don't handle synchronization with extreme rigor.
This brings us straight to that fundamental architectural understanding, the thing that really defines senior engineering judgment. It's not about choosing only processes or only threads, but knowing when and how to combine them. Is that right?
Precisely. High-level platform teams strategically combine both models based on the characteristics of the workload. Processes give you that strong isolation, ensuring that a failure in one subsystem, say a background data worker, won't crash your core user-facing API.
Right.
But then threads, on the other hand, they offer much, much better performance for tasks that need to quickly interact with shared internal state.
Can you give us a concrete example of this combination in action?
Absolutely. Consider a modern Python API server, maybe one built using a framework like Gunicorn or UWSGI. The entire server might be configured to run as, say, 10 separate isolated processes.
Okay, so 10 spaceships.
10 spaceships. This gives the whole platform stability. If one process fails, the other 9 just keep serving traffic, no problem. Now, within each of those 10 processes, the application might then spawn 5 separate threads to concurrently handle incoming HTTP requests.
I see. So the threads are the workers inside each of the 10 ships.
Exactly. And those threads all share the memory of their parent process, so they can quickly access things like configuration data or cached objects. This maximizes the speed inside the process, while the processes themselves ensure fault isolation across the whole system. That is how you design for both performance and resilience.
That makes the distinction crystal clear. Okay, so now let's focus specifically on multithreading. We're moving on to the function and, importantly, the limits of this model. We just mentioned it allows for handling multiple requests at the same time. Can you define what multithreading actually accomplishes when you're using a modern CPU?
So multithreading is the practice of having multiple threads executing concurrently. The real magic happens when you have a machine with a multi-core CPU. In that scenario, these threads can achieve true parallelism.
What do you mean by true parallelism?
I mean, they are literally running simultaneously on different physical cores at the exact same time.
So if I have a powerful 16-core machine, I could potentially split a single large data processing job into 16 simultaneous chunks. And theoretically, that job should finish much, much faster because I'm using all the available horsepower.
In theory, yes. And that's why multithreading is primarily beneficial for what we call CPU-bound workloads. These are tasks where the application is spending 90% of its time executing code and manipulating data that's already in memory. It needs raw processing power, and the workload can be mathematically split up.
What would be a perfect scenario for a CPU-bound multi-threaded task in a platform engineering context?
A great example would be something like data transformation, or complex cryptographic calculations, or maybe background video and audio encoding. If you need to encode a large 4K video file, you can dedicate chunks of the frame processing to different threads on different cores. This just accelerates the job dramatically. You're using every available core, completing a task in seconds instead of minutes.
That sounds like a universal solution. So why isn't every single application multi-threaded? What are the senior-level challenges that this model introduces?
Because it introduces truly complex problems. I'm talking about problems that are non-deterministic, meaning they don't always fail the same way twice.
Oh, that's the worst kind of bug.
It's a nightmare to debug, especially in production. And these issues all revolve around managing that shared state, that shared memory we talked about.
Let's elaborate on those headaches. Let's start with the notorious one, race conditions.
Race conditions are the programmer's nightmare. They happen when 2 or more threads simultaneously try to read or modify the same piece of shared data, and the final outcome is dependent on the unpredictable timing, the race of which thread executes first or last.
Can you give an example?
Sure. If 2 threads try to update a crucial counter at the same time, without proper synchronization mechanisms like locks or semaphores, you could easily lose one of the updates. This results in an inconsistent state. Imagine 2 users trying to buy the very last ticket for a concert at the exact same millisecond. Without strict controls, you might accidentally sell 2 tickets when only one was left.
And then there are deadlocks. That sounds even worse because it sounds like everything just stops.
It does. Deadlocks are caused by improper locking mechanisms. They happen when 2 or more threads get stuck waiting indefinitely for each other to release a resource that they need. Imagine thread A needs lock 1 and lock 2 to proceed, but it only holds lock 1 right now.
Okay.
Meanwhile, thread B also needs both locks, but it currently only holds lock 2. So now neither thread can proceed because the resource they need is held by the other, and they're both just stuck, waiting forever. The entire execution effectively grinds to a non-recoverable halt.
So the insight here is really critical. Multithreading only improves performance when the workload is truly parallelizable and CPU intensive.
That is the key realization. It's what separates effective architecture from just adding unnecessary complexity. If your system is I/O heavy, meaning it spends a vast majority of its time just waiting.
Waiting for what?
Waiting for external operations, like reading data from a disk, waiting for a network API response to come back, or waiting for a database query to return. In those cases, the overhead of creating, managing, and synchronizing all those threads often introduces all this complexity without any real speed benefit.
Because you're not waiting for the CPU, you're waiting for the network card or the hard drive.
Exactly. Spinning up a dozen threads to wait for the same database query just means you have a dozen threads sitting around waiting. But now you also have all the memory and CPU overhead of managing them. It doesn't help.
This realization leads us perfectly to the architecture that solves this I/O problem differently. Asynchronous operations. This is really what enables massive scalability in modern web services and microservices. So how do we define asynchronous operations in this context?
So async operations are a fundamentally different programming model. You initiate a task like a request to an external API or database query, but instead of forcing your program to block its execution and just wait idly for the result,
it does something else.
It immediately continues executing other code. And then when the initial task finally completes, the operating system notifies the program and the outcome is handled later. This is managed via mechanisms like callbacks or promises, futures, events. There are a few ways to do it.
So the single CPU core isn't just sitting there twiddling its thumbs waiting for the relatively slow world of networks and disks. It's being kept fully productive by managing other tasks in the meantime.
Precisely. Let's use our API example. An incoming API request needs data from the database. So the server initiates that database query asynchronously. Now, while the database is processing that request, which could take several milliseconds of I/O wait time, the server's single execution thread immediately context switches to another waiting incoming HTTP request and starts processing that one. It maximizes the utilization of that CPU thread.
That is a massive architectural gain in efficiency for any system that's I/O bound. Why does this model matter so much for public-facing platforms and high-traffic microservices?
Because it dramatically improves the throughput and scalability of precisely those kinds of systems. Public APIs, notification services, microservices. They're almost universally I/O bound. They spend, 99% of their time just waiting for the network or storage or another service. By using async programming, the server minimizes its resource consumption by spending virtually no time idling, which allows a single server to handle tens of thousands of concurrent connections really efficiently.
This brings us to the crucial distinction that every senior architect has to master: the fundamental difference between multithreading and async. They both achieve concurrency, but their approaches, well, it's architecturally opposed.
Yes, and understanding this difference is non-negotiable. Multithreading achieves concurrency by relying on many execution units, multiple threads, potentially running in true parallel on multiple CPU cores. It's a resource-heavy, complex approach geared toward commutation scaling.
Right. More workers for a big job.
Yes, exactly. Async programming, however, achieves concurrency using a non-blocking, event-driven model. It typically uses only a single thread or maybe a very small fixed pool of threads. It's a resource-light approach that's geared entirely toward I/O scaling.
And the classic real-world illustration of this is the Node.js architecture, right?
It is the poster child, absolutely. Node.js leverages a single-threaded event loop. It can manage thousands of concurrent network connections extremely efficiently because for every database query or external API call it makes, it just registers a callback and immediately flips back to service this next waiting request.
So it avoids all that overhead.
It completely avoids the need to spawn a resource-heavy, memory-consuming thread for every single connection. And by doing that, it minimizes resource usage and completely sidesteps all the synchronization complexity that comes with shared memory multi-threading.
So the final takeaway for you, the listener, is that this isn't just some language feature you can turn on. This is a core architectural decision, and it's driven entirely by your application's expected workload.
Absolutely. If you are building a platform API, which is, by definition, an application that waits on I/O async, is often the vastly preferred model due to its superior scalability and optimized resource usage. If you choose a traditional thread per request model for a high-traffic I/O system, you're just introducing immediate, unnecessary bottlenecks and enormous scaling costs. The ability to select the correct execution model for the workload is really the hallmark of effective platform architecture.
Okay, so we've established how software executes internally. Now let's move from the execution model to the deployment model. We have to talk about the cornerstone of modern infrastructure delivery, Docker and containerization. For someone new to this, what is Docker and why did it completely revolutionize how we deploy software?
Docker is a containerization platform that provides a really elegant, robust solution to that ancient and incredibly frustrating problem that every developer has faced.
Well, it works on my machine.
Exactly that. Docker packages an application with everything it needs: the runtime, the specific language libraries, all the necessary dependencies, into a single, portable, immutable, executable unit. And that unit is called a container image.
So the primary benefit then is total consistency. It runs the same everywhere.
That is the core value proposition. A complex microservice packaged inside a Docker container will behave identically in your local development environment, in the continuous integration testing pipeline, in your staging environment, and crucially, in production. This consistency just eliminates an entire class of environment-specific bugs. It streamlines the whole development and deployment lifecycle.
So platform engineers can actually trust that what they tested is exactly what is running live.
That's the goal, yes.
Now, to truly appreciate containerization, we need to look deeper at the container itself and contrast it with its predecessor, the virtual machine, or VM. The architectural difference between a VM and a container is what drives these massive efficiency gains we see today.
Yes, they virtualize different layers of the computing stack. A virtual machine, a VM, virtualizes the entire hardware layer. To run, a VM requires a full, separate guest operating system, like another copy of Windows or Linux installed right inside of it.
So you're basically running a whole computer inside your computer.
That's a perfect way to put it. And that makes VMs inherently heavy, resource-intensive, and really slow to boot up.
And containers are much lighter because they skip that whole layer.
Exactly. Containers are incredibly lightweight because they only virtualize the operating system layer. They're designed to share the host kernel of the machine they are running on. And this is the crucial architectural difference. Because they don't have to carry a separate OS kernel around with them, they use dramatically fewer resources and can start up almost instantly, often in milliseconds.
The efficiency difference must be staggering when you're running a large platform that might involve dozens, if not hundreds, of independent services.
It is. It's a game changer. If you are managing dozens of separate microservices, running each one as a resource-heavy VM quickly becomes cost-prohibitive. You're talking about huge compute and storage bills, and operationally, it's slow because of the boot times.
Right.
Running those same services as containers is just far more resource efficient. You can pack many more containers onto a single host machine than you could VMs, which means you're utilizing your hardware budget much more effectively.
But the senior architectural consideration brings us back to those trade-offs we keep encountering. Sharing the host kernel. That sounds like a potential security exposure.
It is the fundamental security trade-off of the container model, and it's essential for platform teams to mitigate this consciously. A container provides significantly less isolation than a full VM.
So if one gets compromised...
Right. If a VM is compromised, the attacker is generally confined to that virtualized hardware stack. But if a container is compromised, there's a risk that modern tooling works very hard to mitigate, that the host kernel itself could be exploited, and that could potentially impact all the other containers running on that same physical host.
Wow.
So this means kernel security, regular patching, and having stringent container configurations are absolutely paramount for production stability and security.
This naturally makes us ask, what exactly is the operating system kernel? Why is it so fundamental to this whole virtualization discussion?
The kernel is the master control program of the operating system. It is the lowest level software component, and it's responsible for directly managing all the physical hardware resources. The CPU time, the memory allocation, disk access, network I/O. all of it.
So it's the ultimate gatekeeper between the software running on the machine and the actual physical hardware.
Precisely. And the connection to containers is direct and simple. Containers rely entirely on this host kernel for their operation. This is why you have to pay attention to compatibility. If you build a container image for Linux and then try to run it on a non-Linux host, say a Windows machine, that Windows machine has to either provide a comprehensive translation layer or run a lightweight Linux VM under the hood
To satisfy the container.
to satisfy the specific kernel system calls the container is trying to make. The kernel defines the contract that the container implicitly relies upon.
Okay, now let's step outside the server entirely and into the global network. Let's follow a single request. How does web networking actually work when a client accesses a web application? Can you walk us through that sequence step by step?
Sure, it's a complex multi-stage sequence, but mastering these steps really reveals where real-world latency comes from. It all starts the moment you type a domain name into your browser. The very first stage is the DNS lookup. The domain name system resolves that human-readable domain name like thedeepdive.com into the specific machine-readable public IP address of the destination server.
So once the computer has the IP address, it knows where the server is. What happens next?
Next, the client establishes a reliable connection using the Transmission Control Protocol, or PCP, with the server at that IP address. This is the foundation of reliable, ordered communication. Now, if this were just standard, unencrypted HTTP, the request would be sent right away. But in modern platform architecture, the connection is almost always secure. It's HTTPS.
Which means we hit the encryption step.
Yes, and this is the step that often introduces significant overhead, the TLS handshake. This is a cryptographic negotiation and authentication process that establishes a secure encrypted channel between the client and the server.
And it takes time.
It involves multiple round trips between the client and server to exchange keys and verify certificates. It's not instantaneous.
And only after that secure channel is successfully established is the actual HTTP request, the GAT or post descent, and the response finally returned to the client.
That's correct. And the senior insight here is fascinating because it forces us to reframe where performance bottlenecks usually lie. We spend enormous amounts of time optimizing our internal application logic, shaving milliseconds off a database query.
Right, in the code.
In the code. But the reality is that in global scale applications, network latency and the overhead of that crucial TLS handshake often dominate the total request time. They can sometimes exceed the application's internal processing time entirely. If your server is physically located on one continent and your user is on another, the round-trip time alone can be hundreds of milliseconds. Your fast code doesn't matter as much then.
That reality feeds directly into how we achieve global hosting and high availability. If latency and a single point of failure are the enemy, you can't just stick one powerful server in a single data center somewhere.
Correct. True global accessibility requires deploying your application to servers across various data centers and geographic regions. You expose them via public IP addresses and registered domain names. But the key to global scale is managing the flow of traffic efficiently and ensuring redundancy.
What are the key components we use to scale geographically like that?
There are two main components you absolutely must integrate. First, the load balancer. This is essential for distributing incoming user traffic evenly across a fleet of redundant servers in a specific region. It prevents any single server from getting overwhelmed and ensures you're using your resources efficiently.
And the second?
The second is the CDN, or Content Delivery Network. CDNs are these massive, globally distributed networks that cache static content, things like images, videos, or bundled JavaScript files, and they deliver them from a location that's geographically closest to the end user.
So it's a huge tool for reducing latency.
Immense. The content doesn't have to travel across an ocean every single time a user needs it.
The senior perspective on high availability, or HA, is a really crucial concept here. It's about being fault-tolerant, not just being powerful.
High availability fundamentally requires redundancy and automation. It's not about buying one massive, incredibly powerful server that might still fail. It's about having multiple smaller servers spread across different availability zones or even different regions.
Right, so if one data center goes down.
Exactly. This design ensures that if one server or even an entire data center fails, others can immediately pick up the traffic seamlessly. But this necessitates continuous health checks to monitor server status and sophisticated automated scaling mechanisms to dynamically adjust your capacity based on the observed traffic load. If you don't have those checks and that automated recovery, you don't have high availability.
To bring this infrastructure part to a close, let's look at Docker networking and service discovery. Once we have dozens of containers running our microservices, how do they all talk to each other securely and reliably?
So Docker networking facilitates controlled communication, both between different containers and between containers in the outside world. And critically, it allows platform engineers to define these virtual networks that provide necessary traffic isolation.
Can you give an example of that isolation?
Sure. For a multi-tier application, like an API, a processing worker, and a database, you want the workers and the API to be able to talk to each other, but you absolutely want to isolate the database from the public internet. Docker networks let you manage this isolation seamlessly.
And the source mentioned automatic DNS service discovery. That sounds like a massive operational benefit that would simplify microservice code bases.
Oh, it simplifies communication enormously. Microservices are inherently ephemeral. Their internal IP addresses change constantly as containers are restarted or moved around. Service discovery means that instead of having to hardcode fragile internal IP addresses into your code,
Which is a terrible idea.
a terrible idea that will break constantly. Instead, the application simply connects using a predefined service name like UserDB service, and the Docker network layer automatically resolves that name to the correct current internal IP address. The service name stays stable even if the underlying infrastructure is changing all the time.
And the final detail here is leveraging custom networks for environment-specific isolation.
Yes. Creating custom networks allows you to segregate traffic based on environment or security needs. Your production traffic stays on the production network. Your testing traffic stays isolated on the staging network. This prevents accidental cross-environment communication, improves security by enforcing strict boundaries, and just simplifies the overall microservice architecture. It makes it much easier to debug and manage as the system scales up. The senior decision is always to design for isolation first.
Okay, so we've established the execution foundation and the deployment architecture. Now we need to look at what separates a robust professional platform from a flaky prototype. That starts with the definition of a healthy and stable application. What does healthy even mean in a high-scale platform context?
At its core, a healthy and stable application is one that consistently meets very strict availability, performance, and reliability requirements. And crucially, it has to maintain this performance not just under the load you expect, but also under unexpected load spikes. A healthy system has predictable, observable characteristics.
So what are those key operational characteristics we should be monitoring to gauge that health?
Well, first, consistently predictable response times. Users and downstream systems, they rely on low, stable latency. Second, you have to have proper monitoring alerting. If the system is starting to struggle, you must know about it immediately, not when users start complaining on Twitter.
Right.
Third, the ability to scale up or down automatically in response to load. And fourth, the critical ability to recover from failures quickly and automatically without a human having to intervene. That self-healing capability is just non-negotiable for true stability.
Let's focus on the concept of graceful failure. This is where architecture meets the real-world messiness of things. What is it, and how do we design for it?
Graceful failure is the architectural practice of designing your system to degrade predictably when it's facing internal or external problems, rather than simply crashing or timing out or cascading that failure to other services.
So if a downstream service it depends on is slow.
Exactly. Let's say your primary API calls a third-party payment processor, and that processor suddenly becomes slow or unavailable. Your API should not wait indefinitely, burning up resources and holding connections open.
Instead, it should fail fast.
It should fail fast. It should recognize the downstream service failure quickly, maybe by using a pattern like a circuit breaker, and immediately return a controlled, appropriate error message. Or maybe even a slightly degraded response to the client, for example, temporarily removing a non-essential feature from the page.
So the senior insight here is that stability is not defined as the absence of failure, because failure is inevitable.
Right. Stability is defined by the ability to fail safely, predictably, and observably. If you can see the failure, contain it, and recover from it quickly, that is a stable system.
Now let's pivot to API design, comparing the two dominant communication styles we see today, REST and GraphQL. REST has been the standard for web services for, well, decades now.
REST is the veteran, the standard workhorse. It operates on the principle of exposing multiple distinct endpoints, and each endpoint represents a fixed resource shape. For instance, you might have one endpoint for tracks to get a list and a completely separate one for tracks metadata to get the specifics for one track.
It's pretty straightforward.
It is. It's stateless, it's simple to implement, it leverages standard HTTP verbs well, and it's widely supported. That makes it often ideal for public-facing APIs where the simplicity of consumption is the highest priority.
Then GraphQL came along to solve what's often called the problem of overfetching. How does its single endpoint architecture fundamentally differ?
So GraphQL exposes only a single entry point. The power is that it shifts control to the client, to the consumer of the API. The client specifies exactly which data fields they need using a query language. So instead of the server dictating the shape of the data, the client asks for only the specific fields it wants. It's essentially making a controlled database query over HTTP.
That sounds incredibly efficient, but what are the trade-offs? The sources suggest it's efficiency versus complexity.
That is the core decision point. GraphQL's immense advantage is that it eliminates overfetching. A mobile application only downloads the necessary bytes, which improves performance significantly, especially on slow connections. However, this efficiency dramatically increases complexity on the server stack.
How so?
Well, for example, caching is simple with fixed REST endpoints. You just cache the result of tracks. Caching is incredibly difficult with dynamic GraphQL queries because every single query is different. Furthermore, things like performance tuning and authorization enforcement become far more complex because you have to enforce rules deep within the data graph, not just at a simple endpoint level.
So the senior conclusion here is that the choice is context dependent. There's no single best answer.
Absolutely. For large public APIs where client performance is paramount and clients might have very different data needs, GraphQL is compelling. But for internal platform APIs where the governing team controls both the provider and the consumer, REST often remains the simpler model to govern, version, and maintain consistency long term. And remember, communication doesn't end there either. Alternatives like gRPC for high-performance internal communication or message queues for asynchronous workflows, they all coexist in a modern platform.
Now we enter the heart of data integrity with database transactions and consistency. We mentioned the risks of shared state and concurrency, but what defines a transaction in a database context?
A database transaction is defined as a sequence of database operations that must be executed as one single indivisible logical unit of work. This logical unit must either complete entirely, which is called a commit, or it must fail entirely, which is called a rollback. There's no in-between.
And this is governed by the ACID principles.
Yes, the sacred ACID principles, atomicity, consistency, isolation, and durability to guarantee data integrity.
Give us the classic example where violating ACID is non-negotiable and would lead to immediate business failure.
The quintessential example is any monetary transfer or inventory update. Consider an e-commerce platform. The process of creating a customer order and simultaneously updating the product inventory must be a single transaction.
I see.
If the order creation succeeds but the inventory update fails because of a system crash, you have a corrupted, inconsistent state. You've sold an item that still appears to be in stock. A transaction ensures that these two steps must succeed together, or they must fail together, maintaining absolute integrity.
The senior detail here focuses on isolation levels, which is where things get truly tricky when you have thousands of transactions happening concurrently.
Understanding database isolation levels is mission critical in high concurrency systems. Isolation levels determine how and when changes made by one transaction become visible to other concurrent transactions. If you choose an isolation level that is too weak, say, read uncommitted, you open yourself up to severe consistency issues. Like a dirty read, where one transaction reads data written by another transaction that hasn't even committed yet and might eventually roll back. Or even worse, lost updates, where one transaction just overwrites the changes made by another legitimate transaction. Platform teams have to tune this carefully, often trading off a little bit of performance for ironclad consistency, using levels like serializable.
That balance between consistency and performance leads us to the critical architectural choice: SQL relational versus NoSQL non-relational databases.
Right. SQL databases are the traditionalists. They're characterized by fixed structured schemas, very strong consistency guarantees, that strict adherence to ACID we just talked about, and the relational model, where data is linked across tables using foreign keys. They are the undeniable choice when integrity is paramount.
So user authentication, financial ledgers.
Exactly. Complex transactional systems where you cannot afford to be wrong.
NoSQL, on the other hand, prioritizes flexibility and horizontal scale.
Exactly. NoSQL databases are characterized by flexible schemas, document, key value, graph, and they are specifically designed for horizontal scaling across numerous servers. They often favor high availability and, critically, eventual consistency over immediate strong consistency. They excel in scenarios like storing high-volume event logs or caching massive amounts of session data, or analytics where the data structure changes frequently and you prioritize speed and availability over those strict ACD guarantees.
The senior insight drives home that the selection process has to be purely technical, never based on hype or what's popular on a blog.
The choice must be driven by the system's specific data access patterns, the structure of the data itself, and the required integrity model. You would never use a highly scalable, eventually consistent NoSQL document store for financial transfers. And conversely, you wouldn't use a highly normalized SQL database for storing petabytes of unstructured clickstream data that changes every day. You have to match the tool to the transactional need.
Let's define normalization, which is the foundational structural concept in SQL.
Normalization is the formal process of structuring relational data to reduce redundancy and enhance data integrity. The goal is to separate complex data into smaller, discrete, and related tables. For instance, you separate user details from order details so that user's name is only stored once rather than being duplicated on every single order record they place.
Which makes updates simple and ensures consistency.
Exactly.
But the senior perspective acknowledges that sometimes we intentionally break those rules to gain performance. This is the concept of denormalization.
And this is the intentional anti-pattern. It really demonstrates strategic architectural thinking. Overnormalization can severely negatively impact read performance because retrieving common data requires these complex, resource-intensive join operations across many tables. Therefore, denormalization, intentionally adding some controlled redundancy back into the system, is sometimes a deliberate platform design choice used specifically to optimize read speed.
So you accept a small trade-off in update efficiency for a major gain in the speed of the most common user operations.
That's the trade-off, yes.
Finally, let's look at the crucial auxiliary data services that handle specialized data needs: caching and search. Starting with Redis, the champion of caching.
Redis stands for Remote Dictionary Server. It's an extremely fast, in-memory key-value data store, beloved for its incredibly low latency, often measured in microseconds. It's used primarily for low-latency caching, session storage, or as a lightweight, high-speed message broker for queuing small tasks.
What's its primary use case in a high-traffic API?
It is the first line of defense against database load. By caching frequently accessed, slow-to-generate data like complex report results or recently accessed API responses, in Redis, you drastically reduce the number of expensive trips your application has to make to the slower primary database.
So it speeds things up for the user and protects the database.
Yes, it significantly speeds up response times for the end user, and it lowers the operational cost and improves the stability of your primary database.
But it comes with a speed versus risk balance that engineers have to consider.
It does. The fundamental trade-off of Redis is speed versus volatility. Because it's memory-bound, you can only store as much data as you have RAM. And traditionally, it is inherently volatile, meaning if the server fails abruptly, the data held in memory is just gone, unless you explicitly enable and configure persistence, which adds some operational overhead and a slight latency hit.
On the other side of the data spectrum is ElasticSearch. This is specialized for searching massive datasets.
ElasticSearch is a distributed search and analytics engine. It's optimized specifically for fast, fault-tolerant, full-text search and near real-time analytics by indexing vast amounts of data in a highly structured way. And to be clear, it is absolutely not designed to function as a primary transactional database. It is a dedicated read optimization layer.
What are its platform use cases that make it so indispensable?
Its primary roles include indexing massive amounts of complex, often text-heavy data like music track metadata, genres, specific artist names, lyrics, product descriptions, things that a traditional SQL database would really struggle with or take too long to compute.
And it's used for logs, too.
Critically, yes. It's a fundamental tool for central log aggregation and analysis in large-scale observability pipelines. It allows engineers to quickly search trillions of lines of log data to debug production incidents.
So Redis handles the high-speed read cache for known items, and ElasticSearch handles the complexity of fuzzy text searches and deep, near real-time analysis. Both are non-negotiable components in a modern, scalable data architecture. We've built the architecture and structured the data. Now we shift to the engine of delivery, the process by which code actually gets from a developer's keyboard to a user's screen. This starts with the CI/CD pipeline.
The CI/CD pipeline, which stands for Continuous Integration Continuous Delivery, is the automation backbone of the entire software delivery lifecycle. Its fundamental purpose is to automate the building, the testing, and the deployment of applications. It ensures that every single change, no matter how minor, is validated rigorously before it ever reaches a production environment.
Can you walk us through a typical flow? Say a developer completes a feature and initiates a change.
A robust flow begins the moment a developer opens a pull request. That action immediately triggers the pipeline. The pipeline starts with code quality checks and automated unit tests, making sure individual functions work as expected.
Okay.
If those pass, it moves on to integration tests. These verify that the change interacts correctly with surrounding components, like the database connector or a mocked external service. Next up are automated security scans and static code analysis. And only after all of these checks are green does the pipeline build the deployable artifact, which is typically the Docker container image, and then deploy it to a staging or QA environment for final verification.
The mindset here is what really matters. The fundamental goal isn't just about speed of deployment.
No, not at all. The core goal of CI/CD is comprehensive risk reduction and validation. By automating validation at every single stage, you catch bugs early when they are cheapest and easiest to fix, and you prevent them from escalating into major costly incidents in production. A mature CI/CD system is a safety net.
Speaking of deployment, there are different models for how we move that validated artifact to production. The source discusses branch-based versus the preferred tag-based deployment.
Right. Branch-based deployment is simple. Your code is deployed directly from a continuous branch, usually main. It's fast, but it can sometimes lack clarity. The preferred architecture for platform teams, however, is tag-based deployment. This involves deploying immutable versioned releases. You attach a specific non-changing tag to the artifact, something like v1.4.2.
Why is that approach so favored by teams managing critical shared platforms?
Because it provides superior traceability and it ensures reproducibility. When you deploy version v1.4.2, you know precisely which git commit generated that artifact, which tests ran against it, and exactly what is running in production. If you need to perform a rollback due to a critical bug, you don't roll back the main branch, which might contain half-finished work.
Right, you'd be in trouble.
Instead, you just roll back to a known, stable, fully tested version tag like v1.4.1. This is critical for auditing, for operational clarity, and for disaster recovery.
The success of the CI/CD pipeline relies heavily on comprehensive testing coverage. We need to elaborate on the different types of testing that collectively make a platform reliable.
We can categorize testing into several essential layers, forming the classic testing pyramid. We already mentioned unit tests, which are the fast, focused checks on individual functions. Above that are integration tests, which verify the interaction between components. Can the API successfully talk to the database over the network?
And then we have to test the entire user flow.
That's the domain of end-to-end, or E2E tests. These simulate real user behavior, clicking a sequence of buttons, filling out a form, verifying the final output. They ensure the entire flow works from the client interface, through the API, and all the way back again.
And there are other types, too.
Yes. Beyond functional testing, you have specialized types. Load testing validates performance under anticipated stress conditions, and security testing actively probes the system for vulnerabilities, like cross-site scripting or SQL injection.
It sounds like an endless chase for an unattainable 100% coverage metric.
And the mature mindset advises against chasing 100% coverage. Testing, like CI/CD in general, is fundamentally about managing risk effectively. A platform team should focus their testing resources on the most critical, high-risk paths, the login flow, the payment process, the core data storage mechanism. You maximize risk reduction rather than spending 80% of your time writing trivial tests for low-risk, simple functions. You test where failure hurts the most.
Stepping into the operational heart of a modern, large-scale platform, we have Kubernetes. For those who see the name everywhere but don't fully grasp its purpose, what essential operational problem does it solve?
Kubernetes, often abbreviated K8s, is a platform designed for container orchestration. Once you've packaged your applications into Docker containers, Kubernetes is what manages their deployment, their scaling, and their entire lifecycle at massive scale. It automates all the complex, repetitive operational concerns of running distributed systems, which become insurmountable when you have hundreds of microservices.
What are its key features that have made it so dominant in platform engineering?
Its primary features include robust self-healing capabilities. If a container instance fails or crashes, Kubernetes automatically detects the failure and just replaces the instance immediately.
Wow.
It also provides automated horizontal scaling, meaning it can observe traffic load and dynamically scale your API instances up or down instantly. And critically, it facilitates zero downtime rolling updates. This allows platform teams to deploy new versions of a service across hundreds of instances without ever interrupting the user service.
It sounds like a universal solution for operational stability.
It is extremely powerful, but the senior insight comes with a necessary warning. Its adoption significantly increases the operational complexity of the platform team. You're exchanging the manual effort of managing individual servers for the substantial effort of learning, configuring, and maintaining a highly complex orchestration layer itself. You must have the capacity and the specialized skill set to manage Kubernetes effectively, or the cure can become worse than the disease.
Let's briefly touch on cloud provider comparison AWS versus Google Cloud, because many listeners operate in hybrid or multi-cloud environments.
Right. AWS, Amazon Web Services, offers the broadest and most mature ecosystem of services. They are the incumbent leader with enormous feature depth. Google Cloud, or GCP, excels in specific modern areas, particularly its superior managed Kubernetes offering, which is GKE, its data analytics solutions, and its machine learning capabilities, leveraging Google's internal expertise.
For an engineer moving between these platforms, is the underlying knowledge transferable?
Yes, and this is the reassuring point. The foundational core cloud concepts like networking constructs, storage mechanisms, and computing instances, they're based on universal principles. Once you understand the underlying architectural challenge, like how to ensure private network connectivity, finding the equivalent tooling in AWS or GCP or Azure is often just a matter of reading the documentation, not fundamentally learning a whole new architecture.
Finally, in this section, let's revisit asynchronous communication, but in the context of infrastructure decoupling with PubSub.
PubSub, or Publish Subscribe, like Google PubSub or Apache Kafka, is a fully managed event-driven messaging service. Its crucial role is architectural. It allows different systems to communicate without knowing about each other's existence. It acts as a durable intermediary buffer.
That concept of decoupling systems is so central to modern microservices. Why is it so crucial for platform scalability and resilience?
It enables clean, asynchronous communication. When you decouple systems, they become independent. System A publishes a message. System B consumes it. If System B is slow or crashes, System A is completely unaffected because it merely published the message to the queue and moved on. This is critical for achieving high scalability and enhanced fault tolerance, because a failure in one part of the pipeline doesn't cascade and bring everything else down.
Can you give us a detailed, practical example of PubSub in action that really demonstrates this resilience?
Sure. Imagine a massive music platform. When a new track is uploaded, the ingestion service publishes a single event. Track uploaded, 1, 2, 3, 4, 5. That event immediately triggers multiple downstream services for completely independent tasks. Service A starts audio processing. Service B extracts metadata. Service C sends a notification email to the user. And Service D updates the ElasticSearch index.
And if one of them fails?
If Service B fails, the other services just continue processing. The robustness comes from the fact that they're communicating asynchronously through the queue, not synchronously through brittle, direct API calls to each other.
We've talked extensively about infrastructure, networking, and deployment. Now we hit the abstract but absolutely critical layer, the architecture mindset. Moving past the network and the containers requires focusing on the design principles that manage complexity inside the codebase and reduce the long-term cost of change. Let's start with the 5 principles of object-oriented programming, or OOP.
These principles define how we structure software entities to make them maintainable, flexible, and scalable. They're really the rules of engagement for developers who are collaborating on massive systems.
The first one is encapsulation.
Encapsulation means bundling data and the behavior that operates on that data together. You expose only a clear public interface while strictly hiding the internal state and implementation details. Think of it as putting the sensitive internal machinery of a car inside a protective shell.
So we're controlling how the state can be changed. It's about protecting the integrity of the data.
Exactly. The core purpose is to protect the object's invariance, its consistent, valid state. Instead of allowing external code to directly access and modify a critical property like self.userStatus, you require them to use a controlled method, like setStatus. This ensures that validation happens every single time. If someone tries to set an invalid status, you can raise an exception and prevent the object from ever entering an invalid state. This protection makes refactoring internal logic much safer.
The second principle is abstraction. This is often confused with encapsulation. Can you clearly delineate the difference for us?
Right. Encapsulation is the mechanism of hiding the internal complexity. Abstraction is the act of defining the simple exterior boundary that the consumer of your code sees. Abstraction focuses on defining stable contracts interfaces, that expose only what an object does rather than how it does it.
Can you give us an analogy to make that distinction stick?
Sure, imagine a complex industrial machine. Encapsulation is hiding all the gears and wires inside the metal casing, protecting them from outside interference. Abstraction is the simple, clearly labeled on and off button on the outside.
I see.
The user interacts only with that simple on and off label, the stable interface, and does not need to know or care about the millions of internal mechanisms, like encapsulation, that make the machine start. In platform engineering, abstraction is critical because it enables teams to swap out underlying implementations, like replacing the caching mechanism from Memcache to Redis, without affecting any of the consuming code, as long as that stable cache interface remains the same.
Next up is inheritance. This is perhaps the most traditional OOP concept, establishing that is a relationship.
Inheritance allows a class to reuse and extend behavior from a base class. A Stripe client is a type of base payment client. And while that's useful for initial code reuse, it comes with the major drawback of creating very tight coupling between the parent or base class and the child, or derived classes. This leads to the infamous fragile base class problem, where a seemingly minor change in the base class can unintentionally break dozens of subclasses that depend on it.
And that's why the senior insight is always to use it sparingly.
Precisely. Inheritance creates a rigid, deep hierarchy that is difficult to change as system requirements evolve, whereas modern systems really favor the flexibility of composition for managing complexity at scale.
Which brings us to polymorphism. This is a powerful concept for handling complexity and variation.
Polymorphism, which just means many forms, is the ability to treat different objects uniformly through a common interface, even if their underlying behavior differs significantly. The example is simple. Imagine a generic process payment function. You can pass in a concrete object representing Stripe, or PayPal, or a mock testing gateway, and the function executes correctly because all of those objects adhere to the single shared payment gateway interface.
This dramatically cleans up the code logic.
It fundamentally enables extensibility. It eliminates large conditional branching logic. You never need an if payment type is Stripe, else if payment type is PayPal. You just treat everything as a payment gateway. This improves code clarity and drastically improves testability because you can substitute real implementations with controlled, predictable mocks.
And finally, the preferred modern approach, composition over inheritance.
Composition means the complex objects are built by combining smaller, specialized objects. They have a has-a relationship rather than an is-a relationship. So instead of inheriting behavior, an order service has a payment gateway object, and it has a notification service object. These are provided to it, often through its constructor.
Why does that architecture scale better and lead to looser coupling than inheritance?
Composition leads to much looser coupling and a far more flexible design. You can easily swap out the concrete notification service, changing it from email to SMS to a push notification, simply by passing a different object into the order service's constructor. You don't have to change the order service's core business logic code at all. For scalable platform design, composition is overwhelmingly favored because it handles system complexity growth much more gracefully than rigid inheritance hierarchies.
Okay, now we move on to the principles that govern how these OOP elements interact. The 5 solid principles. These are just non-negotiables for building long-term, maintainable systems.
The SOLID acronym is the architectural rulebook. It's designed entirely to manage change and ensure that when a platform needs to evolve, the impact of that change is localized, minimal, and predictable.
Starting with S, Single Responsibility Principle, SRP. This is often misinterpreted simply as keep your classes small.
And that is a dangerous misinterpretation. SRP states that a class should have only one reason to change. It should focus on a single, cohesive concern or responsibility. The size of the class is irrelevant. The bad example is a monolithic order processor class that handles creating an order, validating inventory, saving the order to the database, and sending the notification email, all in one place.
What happens when the business needs to change one of those concerns?
Well, if the database architecture changes, the database team has to touch the order processor. If the email notification requirements change, the marketing team has to touch the exact same order processor class. That class now has 2 independent reasons to change, which can cause conflicts, unexpected regressions, and it needs to be redeployed every week. SRP fixes this by separating those concerns into dedicated, independent classes: an order service, a persistent service, and a notification service.
Next, O, Open-Closed Principle, OCP. This principle states that software entities should be open for extension but closed for modification. How does a team add new features without changing existing stable code?
This is fundamental for maintaining platform stability. New functionality must be added by writing new code, extending the system, not by altering stable existing code. The classic violation is using conditional logic. You have a function with a large if payment type equals Visa block. If you need to add a new payment type, MasterCard, you are forced to modify that existing function.
And OCP solves this using the concept of abstraction we just discussed.
Exactly. By using polymorphism and stable interfaces, you define a stable payment gateway interface that handles a charge function. Now, when you need to support MasterCard, you just create a new MasterCard payment gateway class that implements that interface. The existing stable code that calls charge doesn't need to be touched at all. The senior insight is that OCP is essential for maintaining backward compatibility in critical platform APIs. You have to be able to add new features without breaking your existing clients.
L. Liskov substitution principle, LSP. This principle enforces trust in our abstractions and is often the most subtle but most important for large systems.
LSP states that subtypes must be substitutable for their base types without breaking the client's expected correctness or behavior. In plainer terms, if I promise a function can accept an object of type B, it must be able to accept an object of subtype A, where A is a child of B, and the program must still work as intended without any surprising failures.
What is the most common and damaging violation of this in platform code?
The most dangerous violation is when a subclass fundamentally changes the contract or throws an exception that the base class never declared. For example, if you have a base filesaver class that guarantees its save, method is save, and a subclass encrypted filesaver implements save, but throws a permission denied error that the client code was never written to handle.
It breaks the trust.
It breaks trust in the abstraction. The client assumed the base contract was valid, but the substitution introduces these unexpected failure modes.
Interface segregation principle, ISP. This speaks directly to modularity and coupling.
ISP argues that clients should not be forced to depend on interfaces containing methods they do not actually use. The solution is to use small, highly focused interfaces. Instead of a single, massive database worker interface with 30 methods covering everything from querying to indexing to migration, you segregate it.
Why does this reduce coupling?
Because a client that only needs to read data only depends on the tiny readable database interface. It doesn't need to know or care about the other 25 methods that are used for administration. This reduces coupling significantly, it improves interface clarity, and it reduces the chances of ripple effects when an unused part of a large interface needs to change.
Finally, Dependency Inversion principle, DIP. This is often considered the conceptual foundation of clean architecture and inversion of control.
DIP states that high-level modules, your core business logic, should not depend directly on low-level modules, like the specific implementations of a concrete database driver. Critically, both should depend on abstractions, on interfaces. The abstractions become the glue of the entire system.
This sounds like the mechanism that makes composition and OCP possible in the first place.
It is the ultimate enabler. If the order service, which is high-level logic, depends on a concrete Postgres database class, a low-level implementation, it's highly coupled and very hard to test. If, instead, it depends only on the abstract database interface, you can easily inject a mock testing database or swap the implementation entirely to MySQL without ever touching the core order logic. This improves testability immensely and allows for true architectural flexibility.
We have covered an immense amount of ground today, from the single instruction executed by a thread, all the way to the global orchestration provided by Kubernetes, and finally to the abstract beauty of OOP and the necessity of the solid principles.
Indeed. The journey from a basic running process to a globally scalable, resilient platform really requires understanding all of these layers simultaneously. The core qualities that tie all these senior concepts together are a focus on observability, knowing when and why things fail, backward compatibility extending without modification, failure handling, failing safely and gracefully, and above all, operational simplicity, designing systems that are easy to run, debug, and maintain over a decade.
We established early on a fundamental tension in platform design. Modern architecture favors these lightweight containers that share the host kernel for deployment speed, which is a performance gain. But that sharing inherently reduces the isolation provided by a full VM, which is a security trade-off. This security for performance decision is being made constantly in high-scale environments.
And that brings us to our final provocative thought for you to chew on. Given this fundamental tension speed via lightweight sharing versus security via heavier isolation, what is the optimal balance between operational velocity and ensuring sufficient security isolation in large-scale microservice deployments? And maybe more critically, If the architecture relies on a shared kernel, what new design patterns, what new tooling, or what new runtime mitigations must engineers adopt to ensure that the necessary security trade-off made at the kernel level doesn't become a catastrophic vulnerability at scale?
A question that certainly goes beyond just the tooling. Thank you for joining us for this deep dive into platform architecture fundamentals. We'll see you next time.